So Alan, thank you so much for joining us tonight. Alan is a hardware and software engineer dabbling in audio programming, and Alan is going to present tonight about building a spatial audio plugin.
Yes, so we have this talk pre-recorded, and now I'm going uh, to do that right now. And here we go.
Hi, everybody. Thanks for joining us. My name is Alan Lee, and I am going to be talking to you today about how I created my own spatial audio plugin. Before we get started, I just want to clarify one thing. I am not by any means an expert when it comes to spatial audio. I was introduced to the topic about a couple of years ago now, and I've dabbled with it on and off since then. At the time, I was creating a lot of scripts in Python to do spatial processing offline, and so I thought it would be really nice to have something that acts a lot more real time. I never created a plugin before too, and so I thought this was a really good opportunity for me to get my feet wet, and also an opportunity for me to get more acquainted with the Juice framework. There are spatial audio plugins out there in the wild that will do what my plugin does, but except a lot better, I'm sure. But I just wanted to have the thrill of creating my own plugin. So this talk is called Building a Spatial Audio Plugin, but when you take a closer look at the processing, essentially what it boils down to is you're just applying filters. And so I thought maybe it might be more appropriate to call my talk How to Apply FIR Filters with Extra Steps. But building a spatial audio plugin certainly sounds a lot more exciting. So this slide shows three different iterations of my plugin that I call Orbiter, and I'm just going to take you on a really brief tour of the plugin. Now, unfortunately, I believe due to the way that audio is compressed in a video file, a lot of the spatialization effects get lost. And so if there was audio playing, it would really just sound like it was panning between the left and the right ears. But I still think it's worth it just to show the GUI elements and the general function of the plugin. So this orange circle here that changes to green whenever I hover over it, this represents the audio source. The white circle here represents my head, and I'm faced towards this 0-degree mark. Now this audio source is movable, so if I move it to this area, then audio would sound like it's coming from behind me and to the left. And if I placed it over here, it would sound like it's coming from behind me and to the right. Over here, audio would sound like it's coming from in front of me and to the right. And here, audio would sound like it's coming from directly in front of me. I have this elevation slider here, and what that does is it changes the height of the audio source. Over here, you can set the input and output gain parameters, and I have a few sliders that can change the reverb parameters. We'll get into why this section exists a little bit later on in the talk. Finally, this open sofa button here, when I created the plugin, I wanted the user to have the ability to supply their own spatial data parameters. As things stand right now, this plugin will actually not spatialize audio until you feed in what's called a sofa file. And that file contains data that says how audio should be spatialized. And so we'll talk more about this mysterious sofa file a little later on in the talk. So today I am going to be talking to you about two main things. First, I am going to give a very, very brief introduction to spatial audio and some of the concepts that pertain the most to the Orbiter plugin. And then we're going to go into the nitty-gritty of the plugin development. So let's start with spatial audio. Spatial audio in this context refers to creating the illusion of being able to determine the direction of an audio source, even when it doesn't exist in real life. So let's take an example here with the head and the bird. If we were walking in the woods somewhere and we hear a bird chirp, we are generally able to determine that the bird is probably to the right and a bit above us. And so spatial audio is about recreating that sort of illusion. So there are a number of ways that this illusion can be created. One really popular way that I'm sure many of us are aware of is through surround sound. And that just refers to having multiple speakers placed in different areas and having different bits of audio mapped to those speakers. The other way is through what's called wave field synthesis. And if my understanding of this method is correct, it's a little analogous to how in the Fourier series, complex waveforms can be decomposed into simpler sinusoidal components. And so in here, in the loudspeaker array, each loudspeaker is emitting a simple wavefront, but the collection, the summation of those simple wavefronts will result in the complex wavefront that is emitted by, say, a car or a bird. And so with this method, you're also able to create localization, localized sounds as well too. Finally, the last method is binaural reproduction. This is the method that is actually employed by the Orbiter plugin. And so I'm going to be talking about this a little bit more. So where surround sound used multiple speakers to achieve the spatialization effect, binaural reproduction reproduces spatial audio using only your headphones. And so the idea behind binaural reproduction is to change the time of arrival and the levels of the sound in each ear. So let's take a closer look. In the bottom left here, we have a speaker set up right in front of the left ear. And so when a sound is emitted from the speaker, when the sound is emitted in front of the speaker, the sound is going to reach the left ear first. Now on the journey towards the right ear, on the journey towards the right ear, because the head's in the way, the head is actually going to attenuate that signal. And so what the right ear hears is a attenuated and delayed version of what the left ear hears. And in the middle, looking at this chart here, this is kind of like a graphical representation of what we just talked about. So in blue, we have the signal that the left ear hears, and the orange is the signal that the right ear hears. And sure enough, the right ear gets an attenuated and delayed version of what the left ear is hearing. And so our brain is able to take those differences in time of arrival and levels and determine the location of the audio source. These differences in time and levels is referred to as intraoral time difference and intraoral level difference. And those two quantities are encoded in what's called the head-related impulse response. And that's exactly what we're seeing here in this chart. This speaker emits an impulse, and special microphones fitted in the ears pick up that response. So if we move this speaker around and play impulse response in a 360-degree field and plotted them in a 3D graph, we would get something like this. So these are a collection of impulse responses recorded as the speaker moved around the head. And so on the y-axis, we have the azimuth, the angle where the speaker is placed. On the x-axis here, we have the time. And so starting at 0 degrees, the speaker is right in front of us. And so we see that the time of arrivals is relatively the same and relatively at the same levels. Now, as the speaker moves towards the left ear, we find that the level, the impulse level that the left ear hears is at its maximum, but the level heard at the right ear is at its minimum. Moving the speaker towards the back of the head, we find that the levels and the time of arrivals are roughly the same. And moving the speaker further towards the right ear, we find that the opposite has happened. We find that the level at the left ear is now at its minimum, and the level at the right ear is at its maximum. And moving the speaker back to the front, we see that the time of arrivals are roughly the same, and the levels are also roughly the same as well. So this chart on the right here shows an approximation of the time of arrival of the impulse. And so we see the same thing here. At 0 degrees, the time of arrivals are the same. And also at the back of the head when the speaker is moved closer to the back of the head. As the speakers move towards the left ear, we see that the time of arrival of the left ear is less than the right ear. And after the speaker moves 180 degrees, the right ear now experiences a shorter time of arrival than the left ear. So the time of arrival and level differences are actually not the only cues that your brain uses to localize sound. There's actually a lot of other cues that are used, but this is another big one. It turns out that your outer ear, the shape of your outer ear, plays a big effect in localization as well. And so the ridges and valleys in your outer ear will essentially filter out different frequencies. And so that frequency characteristic is also encoded in the impulse response. But in order to see that frequency spectrum, you will have to take the Fourier transform of the head-related impulse response. And that gives us the head-related transfer function. And for those of you who have been reading a little bit in spatial audio literature, I'm sure this is a term that comes up quite frequently. So it turns out that this frequency spectrum is actually not constant. It changes with the azimuth. And so these two charts here, are similar to the collection of impulse responses that we were looking at in the previous slide, except now we're just looking at the frequency domain version of those impulses. And understandably, when the speaker is moved towards the left ear, a lot of the frequency components do get passed, but when the speaker is moved towards the right ear, because of the shadowing effects of the head, a lot of the higher frequency components get attenuated. And so your brain does spectral processing as well as part of the localization process. So how are HRTFs measured? Personalized HRTFs, the traditional way is by sitting in an anechoic chamber with a speaker in front of you. And then that speaker would play some sort of impulse, and special microphones attached to your ears would pick up that impulse. Then you would be moved by some number of degrees, and the measurement process repeats. Alternatively, you can have an array of speakers, so you wouldn't have to be rotated. And so different speakers at different azimuths would emit impulses. There are also special dummy head microphones like the one we see here that are fitted with anatomically correct models of the outer ear, and those can be used instead of a real person. There is some research in computing HRTFs using only 3D scans of the head, but I'm not quite sure how well that works. And if there's anybody out there who does, please let me know, because I would love to know. So if you have a HRTF and applied it to an audio signal, it turns out that the resulting audio signal sort of sounds like it comes from inside your head. And it turns out that the reverberant properties of a room is actually quite important in externalizing the audio. And so one way to solve this is by moving the measurement setup inside an actual room. And so HRTFs that have room characteristics encoded in it are typically called binaural room impulse responses. And we kind of see an example, measurement setup example right here. Now that we have our HRTF measurements, the question then is, how should they be stored? And if we were working with a small number of HRTFs, 2, 4, or 6 HRTFs, then it's not a bad idea to put them in a uncompressed audio file. But suppose we had 360 degrees worth of HRTFs, each separated by 1 degree. So then that would be 360 times 2 ears. That's 720 impulse responses in total. And so the previous solution doesn't become very scalable. So it would be really nice to have some kind of file format that allows aggregation of those impulse response in one file. And it turns out there is such a file format called the SOFA file format. SOFA standing for Spatially Oriented Format for Acoustics. This is an AES standard, so if any of you are interested in reading the standard, it's AES 69-2015. You can find that on the aes.org website. The SOFA file format is a specification that details how impulse responses should be stored and organized. But impulse responses actually aren't the only information that's stored in the SOFA file. It turns out that information about the measurement setup, so things like what sampling frequency was used, the number of measurements taken, the length of each impulse response, all of that also lives in the SOFA file. So one interesting thing to note is that the SOFA file is based on netcdf, which in turn is based off of HDF5. So you could use the HDF5 library to read SOFA files. Now, if we took a closer look at the contents of a SOFA file, we would find that the data is organized similar to this. Now, this isn't all of the data that's in the SOFA file. These are just sort of the main objects that are of interest to us. So the impulse responses are stored in a one-dimensional array. So if we had 360 impulse responses, or rather 360 degrees worth of impulse responses, then the array size would be 360 times 2 ears times the length of each impulse response. And so you can see that this array can get really big really quickly. Source position and listener position contain lists of the coordinates of the sources and listeners. So for example, if in my measurement setup I only had 4 speakers, one in front, left, back, and to the right, then in the source position there would be a list of the coordinates of those speakers. M refers to the number of measurements taken. N refers to the length of each impulse response. And C is a constant, which refers to the number of dimensions in the coordinates. So us living in a 3 spatially dimensioned world, that number would be 3. There are a number of libraries out there that will read SOFA files, but I wanted to go through the exercise of writing my own library. And this library that I call libbasicsofa warrants a talk on its own, but I am going to be skimming over the finer details and just give a very brief overview of this library. So libbasicsofa is a very bare bones library that will read in a SOFA file and extract its information and dump its contents into memory. There are some functions exposed, so if I, for example, I want to retrieve an impulse response for a certain channel, that is left ear or right ear, for a certain radius, azimuth, and elevation angle, then the libbasicsofa object will calculate where that impulse response is in memory and return a pointer to the start of that impulse response. Looking a little bit under the hood, one of the main challenges to libbasicsofa is because the input parameters are a coordinate, that's the radius, azimuth, and elevation, in order to find where that impulse response will start, there is a mapping that needs to be done to convert that coordinate into an index, an array index. And so what happens is when I pass in a coordinate, first the radius is extracted. The radius is a key for a stud unordered map. And so based on the radius value, it'll return an index to what's called a coordinate map array. So the index of an impulse response for a given elevation and azimuth is stored in a 2D array that I call the coordinate map. Now, for one radius, the range of, say, the azimuth can range from, for example, 0 degrees to 180 degrees, but for another radius, it could range from 0 to 360 degrees. So that range is not constant between two radii. And so for this reason, each radius is associated or has its own coordinate map associated with it. And that's why we store the coordinate maps in an array. So next, the elevation angle, or phi, is entered into a phi map, another stud unordered map object, and it returns the row of the coordinate map where our impulse response will start. And then finally, it'll take the azimuth angle, or theta, goes through another map, and that will return the column. And so using the row and column, you're able to determine the location where the impulse response starts in data.ir, the array that stores the impulse responses. So on to the good stuff. This slide here shows the overall high-level architecture of the Orbiter plugin. So we went through libbasic sofa already, and so an instance of this lives in plugin processor. So plugin processor and plugin editor are the two source files in Juice that we manipulate to create our plugin. So when the source position in the UI is changed, that will trigger the plugin processor to find the corresponding head-related impulse response. And once it finds that, it'll pass it into the HRTF processor. And this is where the input audio is actually applied with, or rather the HRTF is applied with the input audio. Just a quick note about the audio I/O. The input audio into the plugin is going to be only one channel, so it's going to be mono. And because the output is going to be binaural, of course it's going to be a stereo signal. So at its simplest, applying HRTFs can be as simple as applying a finite impulse response filter. It can be as easy as using the Juice DSP FIR filter class, and for the coefficients, the values would just be the impulse response. Unfortunately, because of the features that I wanted to implement in the Orbiter plugin, I can't exactly get away with doing just that. So there are two main ways to implement FIR filters. One of them is the time domain convolution approach, and you would basically implement a filter structure like this. Essentially what this is it's a shift register type of structure, and you would input audio samples one by one, and at each iteration you would multiply the shift register elements with the values of the impulse response, summate them, and you get one output sample. And then you would continue to do this for all of the rest of the samples. The problem with this approach is that it's quite inefficient, and so a better way to do this processing is what's called frequency domain convolution. In this approach, you're taking the Fourier transform of the input signal, and you take the Fourier transform of the head-related impulse response. You would multiply the resulting frequency spectrums together, and then take the inverse to get the resultant time domain signal. So this class of processing in the frequency domain is typically referred to as spectral audio signal processing. And for those of you who have worked extensively with this, I'm sure a lot of the techniques that we'll be talking about here are going to be very familiar to you. So as a start, I'm going to be using frequency domain convolution. And at its simplest, this is what the processing process is going to look like. So from process block, we'll have a block of samples, which will have a gain applied to it. Those samples will get added into a zero padded buffer, and then the contents of this buffer will go through the Fourier transform. And then the HRTF gets applied, the inverse Fourier transform is run, and then the resultant process output signal is sent to the output buffer. Seems simple enough. There's a couple of interesting blocks that I haven't covered yet. One of them is the zero padded buffer, and the other one is the overlap and add block. And so I'm going to be talking about those in a little bit more detail, starting with overlap and add. So overlap and add is a technique that's commonly used, especially when the signal is particularly long, or in real-time systems where we don't know what the future audio samples will be. And so the idea behind overlap and add is this. We take a signal, like this. And then we split it up into blocks of equal size. Then you take one of those blocks. In this example, I've taken block 1, and we run some processing through it, and we get this time domain processed result. Then what you would do is you take this result and you add it into what's called an overlap and add buffer. But you don't start the addition at index 0 in the overlap and add buffer. What you have to do is you have to shift it by k samples. And so what's k? Well, suppose the block size was 512 samples. Because we are working with the second block, then k is actually 512. And so you would have to first shift the process result by 512 samples before you add it in with the previous process block, excuse me. So let's have a look at this in a little bit more detail. We have the signal here up top that we split into 3 blocks. We take the first block and we process it, and we have this resulting waveform. This is the overlap and add buffer. We do the same thing with block 1, and we take the processed output and then we shift it by a block size of samples. And then we do the same thing with block 2. Now I haven't quite added the results of block 1 and block 2 into the overlap and add buffer yet. But when I sum these, then you would get this resultant waveform in green. And so this waveform looks the same as if you had taken these 3 blocks and processed it all at once. And that's sort of the magic of overlap and add processing. One interesting thing to note is that the number of samples in the processed output is not the same as the number of samples in the input. We're going to touch on that a little bit more later on. But essentially what happens is that you would take this sort of tail would get added with the values of the processed block in the next block. And that's where the overlap, part of the overlap in overlap and add comes from. So the overlap and add buffer in theory would be infinite in length, or at least the size of your audio file. But practically speaking, that's not exactly doable. And so the overlap and add buffer is implemented as a circular buffer. And so what happens here is we have process block 0 and 1. Once we process our next block, that gets added into the overlap and add buffer. And then the oldest process block gets erased. Hopefully the contents of that block is added to an output buffer somewhere or is used in some manner. Then when it comes time to increment the empty block index, that just wraps around to the beginning of the overlap and add buffer. So that's overlap and add. The next thing I want to talk about is zero padding. And so remember that in the past couple of slides, the number of samples in the output in the processed output is actually not the same as the number of samples in the input. And so that's because if you have a signal length of p and an impulse response length of q, when you convolve the two signals, the processed signal length is going to be p plus q minus 1. And so the FFT size that you use should be at least that length. Well, why is that? Suppose we had, in this example here, we had a signal of length 128, and our filter response was of length 32. And so if we had used an FFT size of 128, what happens is at the 129th sample, the convolution wants to write the output at the 129th position, but we only have 128 spaces to work with. And so what the convolution does is that it will wrap around to the beginning of the processed output and corrupt the first few samples. And so this phenomenon is called time aliasing. Now, if we had used a size, an FFT size of 128 plus 32, 160, usually we use the next power of 2 available. So if we had used a size of 256, we wouldn't have this issue. And so what does the implementation actually look like? Well, we have these things called zero padded buffers. And so each of these buffers would be of size 256. And so we would take the IR and place that into the zero padded buffer. After the 30-second sample, everything is going to be 0. And that's where the 0 in zero padded comes from. Likewise, we would take the signal and transfer it into the signal zero padded buffer. And so the processed signal will fit comfortably inside its associated zero padded buffer. So these two components are essentially what you need to carry out spectral audio signal processing for FIR filters. But there is one minor detail that kind of throws a wrench into our plans, and that's the fact that the source position can change. And so when the source changes, or rather the position of the audio source changes, that means your impulse response changes. And that means your filter characteristics change. And so when that happens, you run a risk of encountering click noises or zipper noises. And so here on the left, we see that we have an abrupt change of the HRTFs, which gives us this really nasty zipper noise phenomenon. And so there are a number of ways to mitigate this, but the approach that I chose to use was crossfading. And so what happens is I take a copy of the signal, and one copy gets the old HRTF applied to it. Then it runs through the inverse FFT, and the result actually gets faded out by this sinusoidal envelope. Likewise, another copy is applied, another copy goes through, and the new HRTF is applied. Take the inverse FFT, and it's faded in with this cosine signal. And so the total signal is a summation of these faded signals. And so this gives us a much smoother transition in between HRTF changes than if we had abruptly changed them without any crossfading. It turns out, however, that this actually isn't quite enough to completely remove the clicks and the zipper noises. To resolve that, we need to make two small modifications to the way that we perform overlap and add. And so one of them is to window the input signal blocks. So windowing inputs is a common technique used, especially when the filter characteristics are time varying, which is the case when we move the audio source around. And so because when you window the input blocks, the values are of course going to change. And so there's a constraint that we have to meet called constant overlap and add, or COLA. And so what COLA essentially states is if we took one signal and windowed it, and then take another block of signals and window that, if you sum the windowed samples together, then you should get the same input samples as if you didn't have any windowing applied at all. And so that's what we see here. We have one block, and then we have a second block, and when you add them together, you will get this constant denoted in this green line. And so I have this succession of Hamming windows, which when you sum them together, you get a constant. Now the constant doesn't necessarily have to be 1. It just has to be a constant. And that basically just means that you apply a gain or some constant attenuation to the input signal. So note that in order to satisfy this COLA restriction, the constant restriction, notice that the Hamming window does not start at the end of the first input block. Rather, it starts at the midpoint of the previous block. And so this is the other modification that we have to make in our overlap and add strategy. So looking at this in a little bit more detail, we have this original signal. At the top, this is our previous overlap and add method. And it turns out actually that our previous method of overlap and add is actually COLA compliant. Just at the time we were using a rectangular window, and the next block started at the end of the previous block. But in this approach, we take a block of samples, we apply a window to it, and apply the processing that we want to do. For the next block, instead of moving, compared to the previous approach, instead of moving n samples, we move half the amount of samples, carry on with the processing, and so on and so forth. Now, because we're moving in smaller increments, this poses a problem in our processing, because it turns out that if we process one audio block of length n, then the number of usable outputs is actually half that. And so process block would expect n output samples, but we're only able to give half the numbers, half of that. And so our audio input actually needs to be 2 n samples, but process block is definitely not going to give us that. So what do? The solution around that is to have an initial buffering stage. And so here we have the state of the plugin at startup. And so as an example, suppose process block will give us 512 samples and expect 512 output samples. And so our input block length needs to be 2n plus 1, so 1025 samples. By the way, the plus 1 comes from the fact that our windowing function is odd and not even. So after startup, at the first process block call, 512 samples will be input into the input buffer. But because we haven't met the 1025 sample threshold, nothing happens. At the next call to process block, again, samples are added, but we didn't meet the threshold, so nothing happens. Finally, at the third process block call, we finally have enough samples to initiate processing. And so those 1025 samples get transferred into this signal buffer, and an FFT is run, and processing is done, and we get this resulting signal in the overlap and add buffer. Then the first 512 samples are sent out to an output buffer. At the next process block call, 512 samples are added, but we still have a sufficient amount of samples to carry out processing. And so those 1025 samples get transferred, they get processed, and we have an output. So everything's happy and it's chugging along. One last thing that I wanted to note here is previously I mentioned that reverberation is important to externalizing audio. And so I have this is a really basic approach to solve that problem. Essentially what I do is I take a copy of the input samples and I apply it to a reverb filter. And then that reverberated output gets mixed in with the binaural output binaural signal. Now, if we took a look at our final signal flow, it's going to look something like this. A little bit more involved, but still relatively simple, at least in my opinion. You have the samples coming in with gain applied, which gets placed into an input buffer. If the number of samples meets the threshold, then it will start the processing. And so the samples get windowed, the HRTF is applied, and it goes into an overlap and add buffer, which is then transferred to an output buffer. A reverberated version of the input signal is added to the output mix, which then goes out into this output buffer. Now, if there was a HRTF change, then the crossfader would kick in, and the results of that would get added into the overlap and add buffer. So in the next few slides, I want to go through some of the implementation details and look at some of the code in the Orbiter plugin. I wanted to have the ability to change the SOFA files during the plugin runtime, and to facilitate that, I decided to wrap up a libbasic SOFA object and the HRTF processors into a wrapper class. And so when a new SOFA file gets read, this wrapper instance will get swapped with the current instance. Looking at the process block, in this section we take the active the currently active version of the wrapper class. And then here we add the samples. And these two lines here get the binaural outputs. Now, if the plugin was at its initial stage and there weren't enough samples to trigger the processing, then get output will actually return a vector of zeros. This part here is where the output is just copied into the output buffer that process block expects. Now, having a closer look at the add samples, this block here essentially just adds samples into the input buffer. And so when enough samples get added into that input buffer, the processing is triggered, and that's done largely by calculate output, this function here. So let's have a closer look at that. In calculate output, these two lines will actually remove the oldest processed blocks, like we saw in the slides past. This part will run the FFT on the input signal, and this part applies the HRTF and performs the inverse FFT. If there was a HRTF change, then this block of code handles the crossfading, and this block handles the overlap and add process. Now, in theory, you can actually get the output samples from the overlap and add buffer, but I wanted to explicitly have an output buffer which doesn't have the sort of tails that we've seen in the process blocks, since those tails need to have the values of the next process block to be added with. Taking a closer look at the get output function, really the only thing of note here is that we have this have the reverberated version of the input that's added to the processed output. And so that's about it for the implementation. Talking about some of the future improvements that I want to make to the Orbiter plugin. The first one is adding interpolation to in between HRTFs. So some of the SOFA files will have about 1 degree of separation in the azimuths and elevations, but other files may not necessarily have that that degree of separation. Some of them might be 5 degrees or 10 degrees or even more. And so generally when you have a wider degree of separation, you have less correlation between two HRTFs, and that can run the risk of having the zipper or click sounds. And so it would be nice to have an interpolation stage that will give HRTFs at 1 degree increments. The other improvement that I'd like to add is a better reverberation model. Currently, I just use the Juice reverberator, which is based off of Reverb. While it more or less does the trick, there are certainly ways to improve that. Ideally, I would like to have some kind of model which also incorporates applying HRTFs to reflections, but the computing power needed for that is going to be quite high. The next one is more stable SOFA file support. This really just has to do with how I wrote the code. Currently, when a SOFA file gets read, I get a sort of like a default impulse responses. But the way I get those default impulse responses is by specifying a default coordinate. And so that default coordinate might not actually exist in a given SOFA file. And so what happens is that the SOFA file load fails because it gets a null pointer returned by the libBasicSOFA object. The next one is headphone compensation. The headphones will add some spectral coloring to the binaural mix. So it would be nice to kind of remove that spectral coloration. I'm not sure if this makes a huge difference. Again, if somebody out there knows, please let me know. I'd love to find out. And finally, compressed HRTF data files. So SOFA files can get really large really quickly, especially in the case where you are in kind of like a spherical measurement setup. And so if there was a way to compress the impulse responses and reduce the memory footprint, especially in the case where I'm using this in a DAW and I have more than one track using the Orbiter plugin, having a less memory footprint would certainly be very helpful. So that's it for today's talk. Thank you very much for listening to me. If you have any questions or comments, feel free to email me at alee@meowworkshop.org. If you want to have a look at the orbiter and the libbasic sofa code, you can find that in my GitHub. Thank you very much again for listening to my talk.
Great. Thank you. Thank you very much, Alan, for your for doing this. That was fantastic. Where has everybody gone? So I know that Teamer has had to run for a second because he actually had a problem with his computer, so he's probably trying to restart it currently. So we have a couple questions that people are asking. So the first question is from Oren, and he says, what resources are you utilizing for your research? I'd like to begin looking into audio from a programmatic standpoint and also sound theory. So what are some research resources that you use to learn about these?
Yeah, so I think as far as spatial audio is concerned, unfortunately, I feel like I found that there wasn't a lot of resources out there that were very approachable.
Mm-hmm.
I When I first started out, there was this paper in IEEE Explorer. Like it was a paper that unfortunately I think you need to be an IEEE member to download, and it sort of gave like a very basic overview of spatial audio. To build on top of that, I read a lot of papers from like the AES, the Audio Engineering Society library as well. And unfortunately, you do need to have a membership to access those papers. But I will say that like that was probably like the best $120 I've spent as far as like looking for resources went. So yeah, papers, and also the as far as like the audio processing stuff goes, I found the Julius Smith books. The one called Spectral Audio Signal Processing was really helpful when it came down to the implementation.
Amazing. Ismail Salim asks for your GitHub link. So I know that you mentioned it before. Can you just give it to us again, just for people?
Yeah, sure. So it is my GitHub is well github.com/ super kittens.
Okay,
Yeah,
great. And I'll after we get done with this, I'll put the link in the description as well.
perfect.
Nathan Berwick asks, would you run this interpolation from position A to position B or in between each HRIR that is passed?
Hmm. Um, I'm not I'm not sure if I understand the question actually. I think I was following this question actually during the talk. And so I think by the end he was clarifying if I was what happens when I move like the source position from one position to another position that's far away. And the question was if in between those steps the I guess the intermediate impulse responses were used, and that is actually the case. So on its way over, you're going to go through a bunch of HR impulse response changes.
Mm-hmm. Okay, great. And there's a question from Imoni asking if there is a large angle discrepancy between HRTFs, what's the best way to interpolate the signal? If they are 5 degrees apart, how do you separate? How do you simulate 1 degree of separation?
Yeah, that's a really good question. In like a simple case, if we were just changing angles in a plane, I think you can get away with linear interpolation. But things get pretty complicated when you have HRTFs that represent different radii, and also if you have different elevation angles. So how do you interpolate in 3D? To be honest, I actually don't really know the answer to that question. I
Mm-hmm.
did find a paper on how that sort of that triangulation is done, but unfortunately at this time I can't really I won't be able to answer that.
Amazing. There was another question about how big are SOFA files?
So they can range from the one that I was using actually was about 400 megabytes, and I believe that was only on that contains information on just a plane rather than like a whole spherical setup. That one I think was around like 600 to 700 megabytes. So it's a lot of memory.
Wow. Pretty big. And then Alex Grimes has a question if the slides will be available. So would you be able to send me the slides and I can put a link to them in the description as well?
Yeah, for sure.
Yeah, sounds great. So that appears to be all of the questions that we have. Thank you once again, Alan. That was a fantastic spatial audio talk, and I'll probably have to watch through it a couple times to understand everything. But yeah, definitely followed. It was definitely a great introduction.
It was my pleasure. Thanks for listening in.
Yes, thank you. Oh, we do have one more question here, really quick. Oh, he was asking what the for those SOFA files, how much CPU does that take? Is it pretty CPU intensive to process those?
Yeah, when I profile it, the reading and the load took 100% of my CPU.
Wow,
Yeah, so one core was used up completely for that.
amazing. Great. Yes, thank you. Thank you very much, Alan.